All right, ladies and gentlemen, our class recording for today has started. So, over the past week or so, we've gone through the progression. We talked about the differences between constant velocity and constant acceleration, right? And then we talked about, where's a good picture? That picture will work. We talked about when we have something constantly accelerating, how we can figure out the instantaneous velocity. And then we talked about how using the instantaneous velocities, we can figure out how far something goes in each of those individual sections. And then on Thursday of last week, we introduced the concept of free fall. Free fall just being a specific example of constant acceleration where gravity is causing the constant acceleration. And here on Earth, that means that acceleration is equal to 9.81 meters per second per second. Right? And then on Friday, we started talking about this situation, where gravity is causing a constant acceleration regardless of what's happening to our object. And that means that sometimes the acceleration can cause the object to slow down, and sometimes it can cause the acceleration sometimes the acceleration can cause the object to slow down, but other times the acceleration can cause the object to speed up. Right? Good there? All right. On Friday, we used our example of Aunt Minnie handing out $10 bills to illustrate this idea of acceleration, right? That if you start with 0 and you gain $10 per second, at the end of the 4 seconds you'll end up with $40. In question number 3, right, so first we did this one, then we did this one. Even though in number 3 we already started with $20, we were still gaining $10 every second. The acceleration of gravity affects all objects regardless of what they were doing. That acceleration of gravity will change the velocity of the object by 10 meters per second for every second that goes by. And remember, we talked about that these problems here are not taking place on Earth. They're taking place on a planet very similar to Earth that has an acceleration just slightly higher, equal to 10, and that makes doing our math a lot easier to do. All right. When we left off, we were talking about these 3 questions here. Question number 6, question number 7, and question number 8. So we talked about the idea that if we took this arrow and we shot it straight into the air with a velocity of 50 meters per second, the gravity on our Earth-like planet is going to cause an acceleration of 10 meters per second per second. So, on the way up, gravity is going to cause that object to physically do what? Slow down. And slow down by 10 meters per second for every second. So if we shoot the arrow with a velocity of 50, its initial instantaneous velocity is 50. 1 second later, how fast is it going to be going? 40. And then 30, 20, 10, and finally 5 seconds later, its instantaneous velocity is what? 0. Where does that happen? At the apex. Wow, that's a big word. Whoa. So I got an accent and everything, right? At the top, I would have just went with the generic top of the motion. But we can go with something cool like apex. That's cool. So, all right. So at the apex, the instantaneous velocity is 0. And right at the end of class yesterday, or Friday, I guess, we talked about just because an object has an instantaneous velocity of 0 is its acceleration 0. Just because something has an instantaneous velocity of 0, does that mean its acceleration has to be 0? And the answer is no. right? Because acceleration tells us what's going to happen next. It might be currently stopped, but because gravity's still pulling on it, it's stopped now, but it's going to start moving again right away. All right? So, if this is 5 seconds after we release the arrow, we know that its velocity is 0, but just because it's stopped now, gravity is going to start pulling it down immediately. Right? If I draw the next dot right there, all right? 10 meters per second will be its what, Chris? I tricked you on this one. All right, make sure. So Chris said 10 meters per second would be the average velocity. And I gave him an eh. And then he said it would be the instantaneous velocity. And I said eh. It would be something, but it's not either of those two things. It's the instantaneous speed. It will be going 10 meters per second, but, Chris, what would the instantaneous velocity have to be here? Well, nope. Zara. Negative 10 meters per second. Why? Because what does velocity also have to tell us? And direction, right? So, if we go back to our questions about Aunt Minnie, right? After 5 seconds, it takes 5 seconds for that arrow to run out of speed. So, what will be the arrow's speed 5 seconds after we shot it? 0 meters per second. And that happens at the apex, at the top, right? What will be its speed 6 seconds after we shoot it? What will be its speed? 10 meters per second. Okay? Why? Because what kind of a quantity is speed? Start using vocab. It is a scalar quantity, meaning it doesn't tell us direction. Right? Well, you at least knew that scalar was one of the words you have to know. I guess that's it. And then that means after 7 seconds, what would be its speed? 20 meters per second. Because now it's changing by 10, right? Just on the other way down. Good? Okay? All right. Let's summarize the next part, okay, by using this picture. Okay? You have this picture of this guy shooting the arrow, I believe on the previous page before Aunt Minnie. So you might want to add some dots in a similar place that I added the dots. So there's one right here, then there's one right here, then there's one right here, 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 right? Those are the 7 seconds that I have labeled. Okay? So those dots are just representing where that arrow is instead of drawing the arrow each time, right? And I guess you could say it's the back of the arrow if you want to, where the feathers are, if that's, you know, so. And just like is true with a constant acceleration, what do we see about the distance between each dot? What's happening to the distance on the way up? Getting smaller, right? Because on the way up, what's happening to the speed of the arrow? It's decreasing, it's slowing down. It's not going as far every second. But then on the way down, now we start seeing those distances start increasing. Okay? So, question. How high did we shoot the arrow? There. Not quite. Nope. Nope. All right, let's figure it out. You should be able to do this math in your head.
10?
Nope. All right, so let's figure this out. How high do we shoot that into the air? Nope. Okay, so we figured out how to do this when we talked about rolling the ball down the hill, right? Here, when we looked at the whole ramp, whenever we figure out how far something goes, right, we're going to use this relationship, right? Velocity is a relationship between how far it goes and how long it takes us. Okay? Now, because this arrow is slowing down, we can't use any instantaneous velocities here. We have to use an average velocity. What is the average velocity of the arrow on the trip up into the air? There. Nope. Nope. 25 meters per second is the average velocity. How did you figure it out? 0 and 50, right? We know that it was 50 down at the bottom. We know it's 0 on the top. Add those two together, you get what? Well, you add 50 and 0 together and you get 50, and you divide by how many? 2. So the average velocity on this trip is 25 meters per second. All right, do we see where we're going to take this now?
Yeah.
Okay, so we're going to plug 25 in over here for the velocity. It's the average velocity. Do we know the displacement? Do we know how high it went into the air? Ooh, that's what we're trying to find. So that's going to be our question mark. What are we going to plug in for the time?
5 seconds.
5 seconds. Does that make sense? Right? Because that's how long this trip takes. So we're going to plug 5 in here, right? And that means when we solve for this, how high into the air did it go? 125 meters. Does that make sense? How it all went, how it got all those numbers? Is it any different than what we did with the ball rolling down the hill? No. The only thing that changes between the ball rolling down the hill and this going into the air is the value of the acceleration, or I guess, sorry, I'm going to use proper vocab terms, the magnitude of the acceleration. It's the only thing that changes. Does that make sense? So, going back to these Ant Mini questions, all right, here's a new set of Ant Mini questions, all right, that are right underneath the old Ant Mini questions. Yeah, on the same page. Speed is one thing, distance is something else. Where is the arrow you shot up at 50 meters per second when it runs out of speed? What did we just calculate was the height that we shot that arrow into the air? 125 meters. Okay? Good there. In this case, it's just asking you where. Sammy, if it asked you for what quantity would it have to ask you for if it was asked if you needed a direction on it? Velocity, there's another vector quantity. That velocity doesn't tell us where, right? Displacement, right? If it said what was the displacement of the arrow 50 meters after, or when it runs out of speed, then you would have to say positive 125. Does that make sense? Okay. Along those same lines, Sammy, number 2 gets into that a little bit, right? Okay. Frank, good. Sure. 105 is the right answer to the next question. Okay. So, Frank, should I go back to the picture of the guy shooting the arrow into the air? I want you to explain how you got your answer. Okay. So, here's our picture. All right? So we know that it's 125 on the way up. Frank, how did you get to 105?
So it's going 10 meters per second, and it took 5 seconds to get to the top.
Good.
So we were at 1.5, so then going down 10 meters per second. So after 2 seconds, which was 5, now it's 7, then that's 20 meters, and then as soon as you subtract 20, and then it's back to the
Okay. So let's do this over here, right? So Frank, for this 2 seconds, what is the average velocity? From 5 seconds to 7 seconds, what's the average velocity? You're right, by the way. You got the right answer, and I want to make sure that we're using proper terms. So what's the average velocity for that 2 second interval right there, Christina? 10. Technically, if we're talking average velocity, it should be what? Velocity is a what? Velocity is a vector, so the average velocity is actually what? Which way is it going? Right? Okay. And then, Frank, right, we're trying to find this, okay? This little interval is how much time? 2 seconds. So the displacement here is negative 20, right? So Sammy, if we were to ask you for the displacement from 5 to 7, we'd have to go negative 20, okay? But that question on your sheet asked you how high was it 7 seconds after we shot it upward. Well, the first 5 seconds we were going up, the next 2 seconds we came back down, but we've only come back down 20 meters, so we're still 105 meters above where we started. Does that make sense? Good with that? Okay. So, Aunt Minnie drops a penny into the wishing well, and it falls for 3 seconds before hitting the water. How fast is it going when it hits the water? Let's go with our acceleration still being 10 meters per second squared, because that makes our math easier. All right? If it falls for 3 seconds, how fast will it be going when it hits the water? Actually, well, just before it hits the water. Chris? 30 meters per second. Does that make sense, Christian? Okay? This is just the ball rolling down the hill, right? What's the penny's average speed during that 3-second drop? Nope. What did it start as? 0. What did it end at? What's the average between 0 and 30? 15. Does that make sense, Sam? Okay. Oh. All right. And then, that being the case, how far did it fall? Talk to the person next to you. How far did it fall? Go. Do you understand how it's working?
Yeah, that's 15 meters per second.
Yep, that's the city. All right. Did we come up with 45 meters?
Yes.
Okay, good. So I figured you guys were at the point where you probably got that. You were just scared to say the answer. That's why I was like, talk about it with each other, because you'll talk about it with each other, but, you know, not in front of me for some reason. So. All right, good with those three. Okay, now, here we go. Aunt Minnie didn't get her wish, so she gets mad. She goes to do a deeper well. But instead of just dropping the penny down there, she throws it down because she's mad. Right? So, she throws the penny down into the well. So I'm going to go back up to this picture right here. Okay? Actually, here, let me do this. Oh, no, I can't do that. Anyway. Now let's do this. Okay? How's that? I'm pretty proud of this right here. So I'm kind of mad that I have to draw all over it now, but yeah, so. All right, so Aunt Minnie takes her penny. I'll use orange for the penny, okay? And she throws it into the well. But now, instead of just dropping it, it says she throws it with a speed of 10 meters per second. That means that the initial instantaneous velocity is what? The initial instantaneous velocity, you're closer than they are. Make sure we know our terms. The initial instantaneous velocity is not 10, it's negative 10. Because which way is it going? Alright? So here, this is negative 10. Okay? But, what does the acceleration of gravity do? Well, it brings it down, yes. And what happens to it as it's going downward? It's gaining speed. How much? 10 meters per second for every second. Does it matter that it was already moving at 10 meters per second when gravity started pulling on it? No. It always changes by 10 regardless of what it's doing. On the way up, it slows down by 10. On the way down, it speeds up by 10. Regardless of what the initial or the instantaneous velocity is. So if we check in with this thing 1 second later, what's its velocity going to be? Negative 20. Because it changed by how much?
10 meters per second.
10 meters per second. Alright? Second after that, negative 30. Second after that. Here, let me do this. See if this works. Yep. All right, are we good? Finally, it hits the water. Okay? So, question is, how deep is that well? Whenever we're figuring out how deep the well is, we're going to use that relationship. Talk to the person next to you. Figure out how deep this well is. Go. think? Do we need to go through it? How many seconds is it?
Like you said, 4, right? So I know both got it.
Most people, like I said, the couple people I checked in actually did. Do we understand that the time is only 3 seconds here? Right? Yes, it's 4 dots, but that first dot is time 0, right? That's when it first starts. So we have to look at how many intervals is it. It's 3 intervals, and that means we get there. Okay? Does that make sense? We okay there? All right. So the last couple pages. Oh, so to finish off this mini question, okay? How far does the penny go in 75 seconds, or in 3 seconds? It goes 75 meters. Is that the displacement? No, that's actually the what? That's the distance traveled, right? If we wanted the displacement, what would we have to do?
Put a negative.
Negative 75, because it gives us direction, right? Okay, how's that? Okay, the last two pages are pictures of somebody throwing this object up into the air. Okay, one thing we have to remember: this spot right here is always time equals 0. Or we would say that that's the instantaneous initial velocity. Alright? So right here, this would be the instantaneous initial velocity. Okay? Does that make sense? So make sure when we're doing time, right, we consider that to be time 0, but that is the initial velocity. Okay? Just a word of warning. I guess it's a little too stern. Okay? These pictures on the back page might come in handy tonight when you're doing your quiz. Okay? Fill it out based on the acceleration, right? How much does the velocity change every second? What was it initially? How much does it change? What's the next one? What's the next one? We know that at the top, at the apex, what does the velocity always have to be?
0.
It's the instantaneous velocity of 0 up at the top, because that's when we know it hits the top, right? But keep in mind, right, just because the instantaneous velocity is 0 doesn't mean the acceleration is 0, right? Just because it's stopped, it's not going to stay there. It's going to start moving immediately after that. Okay? Good there? All right. Like I said, these pictures might come. Notice that if you look, this one takes how many seconds to get to the top? 3 seconds to get to the top, right? But this one takes 4 seconds, right? 1, 2, 3, 4. Okay? Does that make sense? Sammy, go ahead.
Okay, so the first picture is at the top.
Yep.
The velocity is 0, but the acceleration is 0.
Or whatever acceleration value is at that location, right? If this picture was a picture of an astronaut throwing a ball up on the moon, the instantaneous velocity up at the top would still be 0. Oh. But the acceleration is not 9.81 because that's not the acceleration on the moon. The acceleration on the moon is about 1.6. So that is true that its velocity is 0 and its acceleration isn't. It's just a matter of what is the acceleration at that location. If we were on Earth, 9.81 would be it. All right, good there? Okay. Like I said, those pictures will come in handy tonight when you're doing your quiz. So look for the quiz. I'll actually start working on it now. It won't be done by the time you guys leave, but it'll be there afternoon today. So sorry you have study hall, I know. But. All right, good job today, everybody.